Okay, so now we're moving on to scientific notation, which is a really nice way to write really big numbers. So that's what we're going to focus on today, and then we'll do some more with it later. On this front slide, this is just where you might, just some jobs and stuff where you might see scientific notation. So that's pretty interesting once you start to look in there. And there's way more than just that, but those are just one Google search that I found. Okay, on slide 2, they have some information for us. It's called a single-sided, single-layer DVD. Has a storage capacity of 4.7 gigabytes. 1 gigabyte is equal to 10 to the 9th bytes. So this is an exponent we've been working with. Write a multiplication expression that represents how many bytes can be stored on a DVD. So they're going to kind of walk us through here. They said 4.7 times 10 to the first is the same as 4.7 times 10, which ends up moving the decimal one spot. So here we're going to just follow the same pattern. We're going to take 4.7 times 10 to the second, or times 100, and get 470. Following that same pattern, 10 to the third, 4,700. 10 to the fourth, 47,000. On the other side, kind of the flip of that, says 10 to the first. So that's the same as dividing by 10. That ended up moving the decimal to the left once. So if we divide by 100, it's going to move it twice. So would be 0.047. The third moves it one more spot, 0.0047. We're getting a much smaller number here. 0.00047 because of the 4 spots, and you could watch that. You can move it, your decimal, with your pencil there. Number 3 asks, if 4.7 is multiplied by a positive power of 10, what relationship exists between the decimal point's new position and the exponent? So here was the exponent of 1, and we moved the decimal once. 2, and we moved it twice. 3, we moved it 3 times. So we move the decimal to the right the same number as the exponent. Maybe not the best explanation, but that'll work. And then it asks for the same thing. If we multiply by a negative, what happens to the exponent? Well, we ended up moving it to the left that many spots. We move the decimal to the left that many times. Good. All right, so we do have a vocab word here. So I'm going to go ahead and highlight that, and you can fill it out on your vocab sheet. Scientific notation is written when a number is written as the product of a factor and an integer power of 10. So the factor must be greater than or equal to 1 and less than 10. So we're going to notice here where our number here is the numbers 1 through 9, but any more than 10 it would change it. And we'll see that here coming up in a little bit. This, when the number is written all out like that, that's called standard notation. We've been talking about that in class. And then this is called scientific notation. When we have a number somewhere between 1 and 10, or less than 10, and then a base of 10 with an exponent. So when we're working with scientific notation, if the number is greater than or equal to 1, like this, or a large number if we expanded it out, the exponent is going to be positive. And that means we would move the decimal to the right that many spots. If the number is between 0 and 1, a decimal, like the expanded number is a decimal, the exponent is going to be negative, and we'll see that here on the next slide, and that would mean move the decimal to the left if we were going to write it in scientific notation or in standard form. So moving on here, we're going to write these in standard form. So this is a positive number, which means that this number is going to be much bigger. We're going to move it 4 spots to the right. 1, 2, 3, 4. We'd put in our zeros, so 5, 3, 4, 0, 0. 53,400. This one tells me that the number is going to be a little number and that we need to move it to the left 3 times. 1, 2, 3. 0.00327. Little number, negative exponent. Positive number, this is going to be large, and this tells us to move it to the right 5 times. 1, 2, 3, 4, 5, So we're going to have 742 and then 3 zeros. 742,000. Now all of these are written in proper scientific notation. Proper scientific notation, I'm going to write that over here. So this is proper, which means there's a number, decimal number, and then times 10 to the whatever, 10 to the some exponent. You can write scientific notation differently, like maybe you wrote 61, but that's not proper scientific notation, so we're going to focus on proper scientific notation. So this is a negative. We move it to the left. 1, 2. We're going to have 1, 0, 0.061, and that's a tiny little number. This says move it 2 to the right, which is kind of a weird, why would we write 371.4 in scientific notation? One of those situations where we probably wouldn't, but we're doing it just because we're in that section. Now this one, we're going to reverse that and write it in scientific notation. Proper scientific notation looks like that, times 10 to some exponent. So this is a large number, which tells me my exponent on the 10 is going to be positive. And we need to move it to in between the first two numbers. So 3.725, we have to include all of the actual numbers. We can get rid of the zeros. Times 10 to the, we moved it 1, 2, 3, 4, 5, 6. So 10 to the 6th. This number is a tiny decimal, so that means my exponent is going to be negative. And we have to put it between the first two real numbers. So 3.16 times 10, and we would have moved it 1, 2, 3, 4. So negative 4th. Large number, so positive exponent. 1.414 times 10 to the, we moved it 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. We need to move it there. 8.76 times 10 to the 1, 2, 3. Negative 3, because this number in standard form is little. And this one's weird. Like, why would we not write it this way? But move it to here. 1.14 times 10 to the, we moved it one spot. Negative 1. Negative because it is a decimal. Okay, couple word problems and we're done. Slide 6. Number 5. Refer to this table. Order the countries according to the amount of money visitors spent in the U.S. from greatest to least, so the most amount of money. So this one can be kind of confusing or tricky because if you look at these numbers, 7, you're like, that's the greatest. But if you look at the exponents, the larger exponent is actually the larger number. So that 7 is actually one of the smaller numbers because it has an exponent of 6. So we need to look at the 7s, and 1.03 is smaller than 1.06. So this is going to be the greatest spender. So we're going to label UK, and then, so that was a 10 to the 7th, and our next 10 to the 7th is Canada. Then we go look at our 10 to the 6th, and this one's larger than this one. So we need to go to the next largest, which is Mexico. And last would be India. So India spent the least here, and UK spent the most, apparently. So again, looking at the exponents and not necessarily the numbers out in front. Last one. If you could walk at a rate of 2 meters per second, it would take you 1.92 times 10 to the 8th seconds to walk to the moon. That's a ridiculous number. It is more appropriate to report this time as 1.2. Oh, is it more appropriate to report this time as what I just said, or as 6.09 years? What do you think? Well, I have no idea what that even means, but I do understand that. So explain your reasoning. I'm going to say it makes more sense to use the years because I understand year reference. I want to understand a year reference more quickly than I understand the scientific notation. So basically they're trying to get at, while scientific notation is important, it's not always the most appropriate because we want to understand why would we talk about seconds when that's a lot of years too. All right. Better remain silent and be thought a fool than to speak out loud and remove all doubt. Thanks for listening.